Yeah. Okay, so next up we have Woojin. He's at Duke University. He's going to tell us about Möbius inversions and dynamic data.
Okay, thank you, Amit. Today I'm going to talk about how to extract persistent clusters from dynamic network data using ideas of Möbius inversion. This is a joint work with Facundo Memoli, and we are supported by the NSF grant indicated at the bottom of the slide. And you can find more details about this talk in this archive preprint, which was updated about a few weeks before. So the motivation is topological study of collective behaviors or collection of moving entities. So more specifically, we would like to identify groups or describe the evolution of groups in time-varying metric data. So this picture is taken from work by Uratema and Van Creveld. And this is a snapshot of the video surveillance in an art gallery. The authors are trying to identify groups by analyzing trajectory data extracted from this video. And there are tons of other literatures about identifying groups given a collective motion or collective behaviors. So in this sort of data, actually dynamic graphs naturally arise. For example, in a line of work by a group of computational geometers, including Van Creveld and Woojin, they introduced a notion of group using 3 different parameters. One is connectivity parameter, and another is duration parameter. The other is group size parameter. So for computing groups corresponding to connectivity parameter delta, what you have to do is to see dynamic graphs whose vertices are entities, and whenever 2 entities are within distance delta, we insert an edge. Then we have a delta connectivity dynamic graph. And by looking at that graph, we can extract groups corresponding to that delta connectivity. Another work by Sinover and Ouellette, they studied insect swarms in their laboratory, and they very carefully chose certain connectivity parameter in a systematic way. And by analyzing these dynamic graphs, they were able to characterize insect swarms from the perspective of condensed matter physics. So I'd like to propose in this talk a method to summarize time-evolving clustering information of dynamic graphs using ideas from TDA, specifically using ideas of Möbius inversions. So here we have a dynamic graph over the timeline. And one straightforward way to encode the evolution of connected components is going to be drawing the so-called formigram. So at this time, we have 2 connected components containing vertices 1, 2, 3, 4, and vertices 5, 6, 7, 8. Those correspond to 2 different branches in the formigram containing 1, 2, 3, 4, and 5, 6, 7, 8. And as time goes on, the connected components will evolve. And at this time, we have 4 connected components. Those correspond to these 4 branches. So we identify formigram as before going there. So the formigram looks like formicarium, which means ant house under the soil. And formigram is nothing but a combination of formicarium and diagram. So we identify formigram as a zigzag persistence in the lattice of partitions or in the lattice of subpartitions. So thereby, we are able to define the generalized rank invariant for formigram. And by computing the Möbius inversion of the rank invariant, we can compute persistence clustergram. So persistent clustergram can be viewed as a result of dismantling formigram into linear pieces. Each linear piece is corresponding to some topological feature in the underlying graph of the formigram. And these annotations are explaining which merging events and disbanding events in the formigram are responsible for this linear piece. From persistent clustergram, we can recover the formigram. So that means that persistent clustergram is a complete invariant of formograms. And by forgetting these labels, we can obtain RIP graph and also the zigzag barcode of the RIP graph, and which are very familiar object in TDA. And this pipeline is stable. That means that small perturbations of dynamic graph will result in small perturbations of formograms and the invariance under the formograms. But today my talk is going to be about constructing this persistent clustergram rather than explaining this stability result. Before going further, I'd like to mention one spin-off of our work. So I already mentioned this persistent clustergram. There is a notion of maximal groups given a collection of trajectory data introduced by the computational geometers I mentioned before. And we found that those maximal groups can be also computed using the Möbius inversion by defining a suitable notion of rank invariant for formigrams and compute the Möbius inversion. That rank invariant is kind of dual to the rank invariant we used for defining persistent clustergram. Maximal group diagram is another complete invariant of formigrams. And here, one takeaway is that we can find the notion of Persistent diagram in a context different from persistent homology. I think that was an interesting finding. Okay, let me introduce several posets I'm going to use throughout the talk. First of all, X will be a non-empty finite set. And graph of X will denote the set of subgraphs of the complete graph on X, ordered by inclusion. So suppose that we have these 4 points, then for example, we have these graphs. On the right-hand side, we have the complete graph on 4 vertices, and these are subgraphs of this complete graph. And by subpart of X, we are going to denote the set of subpartitions of X ordered by refinement. Okay, what do I mean by subpartition? Subpartition of X is a partition of a subset of X. For example, if we again have this 4-point set, then these are subpartitions of X. So on the right-hand side, the last 2 partitions are actually partitions of the entire set, whereas the first one is a partition of a subset of X. And what do we mean by this inequality? Well, that means refinement. So the first block of 1 in the first partition, we can find the block in the second partition, which contains this first block. And also the second block in the first partition, we can find the block 1 to 3, which contains the second block. So that's the refinement. Also, 2 blocks in the second partition are contained in the single block in the last partition. So that's what we mean by refinement. And here's a non-example. So these are also subpartitions of X. But you can find that the second block in the first partition here, the block of 2, 3, you cannot find the block on the right-hand side, which contains this block of 2, 3. So we do not have refinement between these. So we have a natural map from graph of X to subpart of X, which is a path component functor. So namely, we just partition the vertex set of graph according to their connected components. So by applying pi0 to these 3 graphs, we actually obtain these 3 subpartitions, right? So 2 blocks are corresponding to 2 components here, and we have 1 component here that corresponds to 1 block in the last partition. And lastly, I'm going to use this zigzag poset as a discretization of real line. So that's the collection of all integers, and between consecutive integers, we are going to insert open interval, and we have an arrow from this interval to the endpoint of the interval. We will view this as a real line, certain discretization of the real line. Now, a dynamic graph will be nothing but a poset map from the zigzag poset to graph of X. So here is a picture. For example, the graph assigned to the open set, open interval 3, 4 is contained in the graph sitting at 3 and 4. So we have this inclusion. And dynamic graphs actually arise from dynamic point clouds by considering the delta Biot-Rips complex and the one skeleton of it. And under bear in mind the assumption about dynamic point clouds, we can make sure that there are only locally finitely many critical points, and we do not care about where the critical points are. So in this talk, I'm going to just assume that critical points are in subsets of integers. So that's why I'm going to use the zigzag poset instead of using other poset. Okay. And the formigram will be nothing but a poset map from the zigzag poset to subpart of X. Here, the partition assigned to open set 3, 4 is a partition defining the 2 partitions sitting at 3 and 4. And formigram, of course, arise by applying pi0 to the dynamic graph. This is actually precisely the formigram we obtained by applying pi0 to the previous dynamic graph. And probably easier picture than the simpler picture than this one would be the picture I gave you before. So two branches before time 1, we have 2-block partition. And as time goes on, we have 4-block partition and 3-block partition and so on. So here are some remarks about formigrams. So we can view formigram as an annotated rip graph. If you remember the rip graph, many of you know that rip graph is a functor from the zigzag set to set category, forgetting about where the critical points are. I'm going to get to this point later again. And also, formigram is actually equivalent to the notion of trajectory grouping structure defined by a group of computational geometers I mentioned before. But I would like to mention that by identifying formigram as a zigzag persistence in the lattice of subpartitions, we are able to define persistent clustergrams and find the connection between this structure with rip graphs and the invariant of rip graphs. So here are some warning signs about formigram. Visualizing formigram is not always easy. This formigram is simple, but once you have many different vertices, then you're not likely to have planar formigram. And minimizing the crossing number of edges is not easy job. And another difficulty is that quantifying the difference between formigram is difficult. There is a notion of Gromov-Hausdorff of distance between formigrams, but computing it is difficult. So for these reasons, we would like to further summarize formigrams. And one of them will be persistent clustergram. So for that, let me introduce the lattice structure of the subpartition of X. So we have meet and join. The meet are going to be the coarsest common refinement of multiple partitions. And the join are going to be the finest common coarsening of multiple partitions. For example, if we have this 3-point set in the underlying set, then this is the Hasse diagram of subpart of X. And if you look at these two partitions, for example, then the coarsest common refinement is going to be this partition. And finest common coarsening will be this top partition. And let me introduce one more notation, the collection of all intervals of the zigzag set. So we have this zigzag set. And when you collect these 5 points, then that 5-point collection will be denoted by this closed interval 0, 2, because that's what we obtain when you union these indices. And likewise, we use these notations for denoting these collection of points. Okay, so angular bracket AB will denote one of these type of interval. Now, suppose that we have a formigram and we have an interval, and then we can compute the coarsest common refinement over that interval and also finest common coarsening over that interval. For example, if we have these 5 points and we have a formigram over these 5 points, and this is an example of formigram, when we zoom in this closed interval from 1 to 3, we have this zigzag persistence of partitions. And when we compute the coarsest common refinement, we have this 4-block partition. And when you compute the common coarsening of this 5 zigzag diagram, then you can find that this 2-block partition is the common coarsening. Now I'm gonna define rank invariant for formigram. For that, we will consider the coimage of the meet in the join. So we have this 5-point interval, then we are gonna have join and meet. Those are partitions, and the partition corresponding to meet will be refining the partition corresponding to the join. Actually, this block B1 is contained in block C1. These 3 bullet points are the same as 3 bullet points in C1. And B2 is contained in C2, and B3 is also contained in C2. These bullet points are the same bullet points. Now, I'm going to consider something between them. So I look at the underlying set of the meet, and I'm going to use the boundaries from this join to define the partition in this over these points in the underlying set of meet. So these 7 points, but notice that these boundaries are coming from this boundary. So I'm pulling back the equivalence relation in the join to the meet. Actually, this coimage is not in the category, subpart category, we have a larger category which contains subpart of X, and this coimage is computed in that category. And one remark is that if the join and meet have the same underlying set, then this coimage is not different from the join. For example, in the previous page, we saw this formigram and the meet and join here have the same underlying set. Then when we compute this coimage, that's not different from the join. Now the rank invariant will be defined as the map which sends each interval to the coimage over that interval. And that's the rendition of the generalized rank invariant for zigzag persistence in my previous work with Facundo Memoli. And the Persistence clustergram will be defined as the Möbius inversion over the set of intervals. So we have this familiar plus minus formula we saw in the Amit talk. So these plus minus operations will be defined soon. It will be explained soon. It's actually operations in the free abelian group generated by all the non-empty subsets of X. So let me give an example. So we have this 3-point set, and we have a formigram over this 3-point set. Then we have this diagram of partitions over 5 points from 4 to 6. I'm going to compute the diagram corresponding to the open interval 4, 6. Open interval 4, 6 correspond to these 3 points in the middle. And we can find that these partitions are the same. Therefore, the coimage is not different from these partitions. So I have just this same coimage, but instead of writing this block, the partition in the same as before, I'm going to write it as a sum of 2 blocks. It's a formal sum. And now we consider these coimages over intervals that correspond to the interval obtained by adding 1 left point to the interval. And these other intervals as well, we compute the coimage. Then what you have is this formal sum. Then the last 2 terms will be canceled out. And the first 2 blocks will be written as a single partition for just simply shortening the length. Then when we compute this diagram computation, what we're going to have is this picture. So we have 3 intervals. Other than these 3 intervals, the diagram values are 0. And you can find that these intervals correspond to topological features in the given formigram. And over this interval, the annotation is given here. And you can find that these 2 blocks are merging at time 2. And that is actually explained in this annotation. 2 blocks become 1 block. So after minus sign, we have the resulting 1 block. And also between 4 and 6, we had 2 partitions before, but beyond 4, 6, we have 1 block partition. That 1 block will be denoted after this minus sign. And over this entire interval from 0 to 8, we have 3 entities in all partitions. So those 3 entities are collected in this single block partition over the interval from 0 to 8. Other than this interval, the diagram vanishes. So I mentioned before that formigram can be recovered from persistent clustergram. Here is the proposition. So at time t, we can compute formigram value by adding the diagram values corresponding to intervals which contain the time t. So here is an example. We have a dendrogram, which is a specific case of formigram. At time t, we have 3 block partition that is written here. Then we can observe that there are 3 intervals containing this time 2. Then we are going to add up the annotations corresponding to these intervals. There will be these intervals. Then we can cancel out these 2 blocks, and we can cancel out these 2 blocks. And we end up with the sum of these 3 singleton blocks. That's the same as formigram value at time t, time 2. Now, this is analogous to the fact that when you have a standard persistent module, for computing the dimension at specific index, we can find it by counting the number of intervals containing this specific index. But actually, this remark is more stronger than this this standard fact, because we are really recovering the entire formigram. By knowing its value at time t, the formigram value, we can recover the entire formigram structure. But that's not the case for persistent module. Okay, here, let me give a remark about forgetting labels. So by forgetting labels of formigram, we obtained riprap. That's actually post-composing a functor. If you remember, formigram is a zigzag, it's a functor from the zigzag poset to subpart of X. Here we have a collapsing functor, which sends each subpartition to the set. We are post-composing this functor to the formigram, then we obtain riprap. So how this functor works? So we have this 3-block partition and 2-block partition. We have this refinement. Then these 3 blocks will correspond to 3 points in the set. And these 2 blocks will correspond to 2 points in the set. And depending on which block is contained to which, we just assign arrows. Then what we have really a set map between sets. Okay, and how do we go from persistent clustergram to the silhouette of the persistent clustergram? That looks like zigzag barcode, but actually this silhouette is not always the zigzag barcode. The way to go from here to there is to look at this annotation, and this annotation in the first interval, we have 1 block partition. That's 1, so that 1 becomes the multiplicity of this interval. And in the annotation for the second interval, we have 2 block minus 1 block. So 2 minus 1 will be the multiplicity for the second interval. And for other intervals, we all have 2 block minus 1 block annotation. So 2 minus 1 will be the multiplicity for these intervals. Yeah, that's we are applying counting homomorphism, and this silhouette is actually not always the zigzag barcode of riprap. There is some condition we need to guarantee that silhouette coincides with zigzag barcode. And these silhouettes are stable in the erosion distance under the mild assumptions about formigram. So here is a summary. So I defined these invariants and the persistent clustergram specifically, and briefly explained the relationship between formigram and persistent clustergram with ripraps and zigzag barcodes. And I also mentioned this maximal group diagram, a spin-off. Some open questions. So we were able to classify dynamic graphs using the zigzag barcode that at the bottom of this panel, the bottom panel before, but we were wondering whether there is a annotation sensitive bottleneck distance. I think this is related to what Amit mentioned before. So we would like to find such distance and find the relationship between this annotation sensitive bottleneck distance with other known distance. And also find an efficient way to compute persistent clustergram. There will be also question you're interested in. Thank you for paying attention. I'll be happy to receive questions. Yeah, who raised hand? Hans?
Hello. So
Hi.
I wonder if you could say anything more about the co-image construction.
Oh, yeah. So co-image construction, for that, we need to define category or partition, which is not relevant to underlying set. So what we did was, okay, that's the collection of partitions of arbitrary sets. The map between partitions is defined as the set map between elements, the underlying set of the partitions, but that map should be injective and that should be block preserving. That means that if 2 elements are in the same block in the domain, then they must be also in the same block in the image partition. That is the category that we consider, which contains subpart of X, and we computed co-image in that partition, in that category.
And by co-image, you mean it's yeah, some object modulo a co-kernel of something? or
Yeah,
is it
so
not?
right, so the analogous to the co-image in vector space category. So that is when you have an arrow from A to B, the co-image of that arrow is defined as the epimorphism from the domain to another object, which satisfies some universal property. So that's the definition in category theory. Yeah.
Thank you.
Yeah. Thank you. And Parker?
Thank you for the talk, Woojin. Can we look at your last slide again? I have a much more naive question to make sure I'm understanding. Sorry, next to last slide. That's my bad. So this zigzag pose set for at least for this dynamic graph situation that we're thinking of. Should I think of these endpoints, the graphs that occur at these endpoints as being kind of formal compared to like the data? And let me clarify what I mean by that. So you're thinking of like a crowd moving around, right?
Yeah.
And these are the different graphs in the open intervals, to my understanding, right? And then at the endpoints, you have these transition points. Is this the correct interpretation?
Yeah, on the open interval, the graphs are the same, and changes happens at the critical points.
Right. And so at these critical points, do we, like, we kind of don't necessarily observe the graph at the critical point in the actual, like, if you had a crowd of people, they did not necessarily attain that configuration. Is that correct? It's just kind of a formal, or is it always one of the endpoints?
We really obtain that exactly graph. The graph that is obtained by bilateral sweeps at that time precisely, and we look at the one skeleton of bilateral sweeps corresponding to that connected parameter. We find that graph precisely. It's not formal.
Okay. Got
Yeah.
it. Thank you.